My name's Paul Crosby. This summer I worked in cooperation with Cancarb to do a presentation or a study on the influence of Thermax N990 in various compounds. So the reason we did this study is to measure hydrogen permeability for a new application. Again, we're working with Cancarb primarily on this. They're helping support us with funding and also supplying us with some materials. And then we're also working with Arlanxio. I'm sure most of you are familiar with Arlanxio. Arlanxio is again helping supply us with some materials, and also they're helping us out with some starting formulations. So who is Cancarb? Cancarb is a leader in thermal black for innovation, manufacturing, and marketing. For the last few years, Cancarb has helped fund and participate in several innovation studies. They're very into getting data and into getting innovations rolled out through them. They also currently have the largest facility of its kind in the world. It's pretty impressive. We've got some good pictures on the website of it. So the actual material application. So hydrogen-powered vehicles are a big up-and-coming thing. Toyota is investing a lot of money into them currently. And with this also comes the infrastructure to support these hydrogen vehicles. So with this, we're going to get hoses, bladders, and seals that all need to be made out of rubber. And also for the infrastructure, for the storage and delivery side of the infrastructure, we're also going to need, again, these hoses, bladders. So permeability. What is permeability? Permeability is the quality of a material that causes it to allow a liquid or gas to pass through. So a big thing to keep in mind when I'm talking through all this, we desire a very low permeability. We want the least amount of gas as possible to get out. So the big reason we care about permeability is safety. Hydrogen is very dangerous. But hydrogen, when it mixes with oxygen, is incredibly dangerous. Some of you guys might recognize this as the Hindenburg. It was a blimp that was filled with hydrogen, and sadly, due to some engineering mistakes, it was one of the biggest disasters of its time. And then the second reason we really care about permeability is fuel economy. If your hydrogen's going through your seals, you're losing out on fuel economy. More or less, you're letting your fuel float away. So with every study, we like to start with a scientific method. We like to start with either a problem or a question. So for this study, we started with a question: what are the effects of N990 and that high aspect ratio talc on specific polymers? So before getting to the hypothesis, we like to do a lot of background research. As Rick always says, we like to be prepared before we just jump in and start running tests. So we read through a bunch of papers pertaining to different polymers and different filler loadings with concern to hydrogen permeability and also oxygen permeability. After going through all this research, we made the hypothesis that high loadings of N990 in ratio with high aspect ratio talc will help reduce the compound's permeability to both hydrogen and oxygen. And then later on in this slideshow, I'll go through the experiment analysis and conclusion side of this. So the polymers that we selected brominated isobutyl, both a sulfur and a resin-cured system. We selected acrylonitrile rubber, or NBR, and we also selected epichlorohydrin. We selected these rubbers because they are the most promising for both oxygen and hydrogen permeability.
Did you mill the epichlorohydrin?
No. For the fillers selected, we went with Thermax N990, which is a thermal carbon black, then carbon black N330, which is, again, as Montana said, one of the furnace carbon blacks, and a high aspect ratio talc. So for the actual morphology of these, you can kind of think of N990 as like a little, almost like loose balls or loose grapes. And then carbon black's kind of like a grape cluster that's really big and like complex agglomerates. And then high aspect ratio talc's kind of like platelets. So a big part of permeability is something called the tortured path or tortuous path. It's more or less making a longer and a harder path for the molecule to travel before it escapes through the polymer. So to get a longer path, you introduce things like high aspect ratios or varied particle size. With the high aspect ratios, you can see it kind of has to go around all these platelets. This would be like something like silica or talc would do this. The reason we didn't use silica in this study because silica's poor bonding with certain polymers actually leads to a decreasing permeability or increasing permeability, making it a worse problem. And then with the varied particle sizes, pretty much what you do is you get big particles, and you start filling in the gaps with smaller and even smaller particles. So you get this path that kind of delineates and weaves through. To create a more tortuous path, we introduce impermeable obstacles. So most fillers are impermeable to both hydrogen and oxygen, so that's what we care about for this study. And then the filler to bonding is really important as well. So as Montana mentioned earlier, silica and even like talc or clay has a bit harder time having bonds to the rubber, like intermolecular bonds. But the carbon black, because it's carbon-based, same with polymers, it's very easy to get good bonding between the two. And then the last thing is lower internal polymer mobility. This is kind of why we selected the polymers we did. A polymer whose chains don't move by each other is going to have better permeability properties. So the less internal movement, the better for a polymer, at least for this application. So for the design of experiment, we went with a 4x4x4 experiment, 4 polymers, 4 ratios, and then 4 different loading levels. So in this little example, each one of these cubes is a single run. So 4x4x4, 64 runs, which it's not enormous, but it's a pretty big experiment. So to filter through these 64 runs, because to be honest, hydrogen permeability testing is not the cheapest thing. And to do 64 runs of it would not be super advisable. We created some filters to get down to the most promising polymers. So what we did is we started with the physical properties, such as tensile and compression set. So what we're doing is, if we have a tensile that's not high enough, there's no reason to make a sealer hose out of it, even if it has good hydrogen permeability, because your sealer hose is going to blow out. If your hose blows out, no matter how good your hydrogen permeability is, it's not going to protect you. And then we also went into processing tests with the RPA. So at a lab scale, we can process some of the stuff that's a little bit more harder to process. But in mass production, we want a polymer that's able to be processed fast. Speed is a very big thing in cost reduction on a large scale. And then the last filter that we use is the oxygen permeability test. So oxygen permeability is not a one-to-one with hydrogen permeability, but it is a good enough model that we can take the best from the oxygen permeability, and we should see almost identical trends in the hydrogen permeability test.
And it's much cheaper.
And it's, yeah, well, it's free for us. It is much cheaper. So for the first test, it's tensile, more or less, as Montana said, it's stretching to a point and seeing how much energy it takes to actually snap the sample. So this is important, again, like I said, because we want to make sure that our hoses or our seals are going to be able to hold up. So for this, me and Rick were able to come up with a figure of 1200 PSI is the minimum allowable for this study. It's just a good round figure. It's a lot of the industry uses it. For the next test, we use compression set. Again, Montana went over this, where you compress a sample, and then you see how much by percent it demorphed. So we did a compression set for 70 hours at 100 degrees C. So this determines the sealing potential. So for compression set, if it squishes down and doesn't recover, you're going to have your hydrogen or your oxygen or whatever you're trying to seal. It's just going to blow through between the rubber and the metal. So it doesn't matter what your permeability is if that's bad. And again, for this, we chose 25% as the maximum allowable for this study. So that's not this 25% that you squish it. It needs to morph only by 25% of that. And then for the rheology, again, we did standard rheology. This is just the STM D5289. This is the one that gives you like MLMH, TC90 and such. And then the second rheology that we did was strain sweeps. We did this more or less to model dispersion. This isn't used as much as a filter as it is to see that we did our job correctly and that the rubber is properly mixed. And then that's the way that you do that is by comparing G prime at high and G prime. So for, you got something?
That was pack density that we were looking at there, right?
Yeah. So for oxygen permeability, this is a pretty standard test they use. It helps to model the hydrogen permeability for us. So the way they do this is they just float oxygen through the upper chamber, and then through the bottom chamber they float nitrogen through, which nitrogen's not going to permeate. And then the nitrogen picks up the oxygen and sends it to a gas chromatographer. The hydrogen permeability works identically. It's got a little bit tighter constraints on what the actual apparatus to use it is. This is a setup that is very common in the industry. This is the actual test chamber. So achieving good hydrogen permeability is a very hard thing to do. Hydrogen is the smallest molecule possible, and this creates problems because it can shoot through most rubbers. So that's again why we care about the permeability. So permeability is a product of solubility and diffusivity. Solubility is more or less how the rubber accepts in the liquid or the gas, and then diffusivity is how it like spreads through. One additional thing is the absorption of hydrogen. So the reason we're not using the high aggregated the carbon blacks in mass is because although they do create a more tortuous path, they also have small voids in them that you can't disperse properly through, and these small voids will trap the hydrogen. So you're not permeating the hydrogen through, you're not necessarily losing it, but if it's in your seal, you can't use it for your fuel, so it's useless to you. So where are we now? So currently, we've done a lot of preliminary testing. So at the beginning, we thought about using chlorinated butyl rubber. With some cooperation with Kevin Kabalba, we decided to scrap this. We found out that it's not going to decrease our permeability by any reasonable value, and it's going to give us worse properties than what we can get with the brominated butyl. So then we played around with some hard clay. We found that hard clays, just through our studies again and some cooperation with Daryl Mayer, we found out that hard clay is just not going to give us the same properties that we can get with N990 and high aspect ratio talc. So what we did next is we started trying it with talc, and then we figured out the talc's great. It's going to help us with permeability, but talc and N990 alone aren't going to be enough to keep a constant duro or be enough to get high tensile properties that we need. So what we did then is we decided to add a small amount of reinforcing carbon black N330 to help us get to the physical properties required. So for the future, we plan on running through the rest of the filter. So as of right now, we're in the tensile and compression set area. And in the future, we're going to run through the processability tests, which we've already done some of, and then mainly the oxygen permeability and hydrogen permeability tests is what we have left. And then I think Rick, you and Kevin Kabalba are planning on writing a ACS paper on it.
Yes, we are. Or 2019.
So I'd like to give a big shout out to Cancarb for making this possible and making my internship here this summer possible. They're really good people to work with. I've had a good time working with Ross. And then also the lab crew, they're really good people. They've taught me a lot, especially Elias. And then just everyone else here, you guys have made it a really enjoyable experience. And I definitely am going to look back on this one.